This is the third section of our Homework 2 tutorial, two measures of unrelatedness. In particular, we will talk about two measures of unrelatedness between two random variables. Suppose we have x and y as random variables, and we define the covariance between xy and x and y as sigma xy, which equals to the expected value of the product between x minus mu x and y minus mu y. We have mu x and mu y as the mean of x and y respectively. So what does this mean? So suppose we have a sample of x, y, and we plot them on the graph. So most of the points are located on the upper right quadrant, and we will see that x minus x bar or x minus mu x is positive here for all points on the upper right quadrant, and y minus mu y will be positive as well. So this gives us a positive value of the mean difference product, and it's similar here on the lower left quadrant. So both mean difference will be negative, but the product of them will be positive. So for any given sample of x and y, if most points are located either on this quadrant or this quadrant or both, then we would see that x and y has a positive correlation with each other. And if for another sample all the points are located along this diagonal, then we would observe a negative correlation between x and y. So that's what the covariance means. And it's similar for the coefficient of correlation. So we define the coefficient of correlation rho xy as the covariance of xy divided by their standard deviations. So we can say that the coefficient of correlation is a standardized covariance of x and y. And if they are equal to 0, then we see the random variables x and y are uncorrelated with each other. In particular, if we run, so suppose we have x and y, and we run a regression of y on x, and we know that from the coefficient formula, beta 2 equals to the covariance of x and y divided by the variance of x. And if we compare the coefficient of correlation with the regression coefficient, we see a lot of similarity between them. So it's all the covariance of xy divided by either the standard deviation of x or the product of the standard deviation of x and y. So they are both of them are measures of the linear relationship between x and y. There are some points we need to be careful about. So covariance depends on the units of measurement, but correlation, the coefficient of correlation is unit free. So what does that mean? So if we look at these two graphs, basically they are the same, except that the x here is in a different unit. So we see here x is measured in a unit of 1, but here x1 is measured in a unit of 100. And if we look at the covariance of x and y and compare that with the covariance of x and y and x1, then we see that we have a higher covariance here. But because these two graphs are exactly the same, and a high unit of measurement gives us a higher covariance of the two random variables. This is not what we want, because we want to have a consistent measure of correlation between two random variables. So they shouldn't depend on the unit measurement. and that's why we get the coefficient of correlation. So we also have two same graphs, but here and x and xy, x1 are in different unit of measurements, but we see here the correlation coefficient are the same. So that's why we say the coefficient of correlation is unit free, because it gives us a consistent measurement of the correlation between x and y. And the other thing we need to be cautious about is that both covariance and the coefficient of correlation are measures of linear relationship between x and y. So suppose we have a nonlinear relationship between x and y, and they are clearly, they do have a relationship, and we can see that this is a parabola here. X equals to x, y equals to x squared. But the coefficient of correlation is 0 in this case. And similarly, it looks like a parabola, but we observe the coefficient of correlation equals to 0 as well. So they are not good measures of relationship between x and y if x and y are nonlinear. If their relationship is nonlinear. So that's why in this question, in the question of 3.16, that statement is false, because even if the covariance of x and y are 0, it doesn't necessarily imply that they don't have any relationship between with each other. So covariance and the coefficient of correlation are the first measure of unrelatedness between two random variables. The other one is independence. So if x and y are independent, and g1x and g2x are two functions of x and y, then if the expected value of g1x times g2y equals to the expected value of g1x times the expected value of g2y, then we would say that x, y are independent. So what does this mean? So independence between x and y is equivalent to stating that every function of x with finite variance is anchored with every function of y with finite variance. If we compare this to zero correlation or zero covariance between x and y, we would say that zero correlation is equivalent to stating that every linear function of x is anchored with every linear function of y. So independence is a much stronger property of x and y than zero correlation. So independence would imply that the covariance or the coefficient of correlation is 0 between x and y, but the converse is not true. So even if they have 0 covariance, it doesn't mean that they are independent. So in the later chapters, we would often talk about the covariance, whether the error term is independent from other regressors or not. So sometimes we would write the covariance of the error term and the regressor as 0, but it doesn't mean that they are independent. So just pay attention to this property when we study the regression assumptions later on, because that's a very important assumption for regression analysis. So this is the end of this section.